Thank you. And good afternoon, everyone. Can you hear me just fine like that? Yeah? Cool. So yeah, I'm Irina, and for the past 10 years, I've been working specifically on computer vision, object detection, object segmentation, that kind of stuff. And currently at Viorama, we're developing an app that does augmented reality, which essentially means applying digital effects to a live video, a real live video that you could be recording with anything, for instance, your phone. So that's used for things like overlaying information on, say, mechanical parts at some workshop, but it can also be used to do deeply satisfying things, such as this. So in order to punch this guy's head in, you first need to find a head, right? Or his body, and then extrapolate. In any case, when your subject is facing the camera, it's computer vision techniques, the traditional ones, tend to work fairly nicely. You can get a face detector fine on this kind of face. She's facing the camera, she's not too far away. That's fairly, I'm not going to say easy, but it's done. But when the subjects are rotated away from the camera, or there's wonky angles of that camera, or if they're partially outside the frame, or they're occluded, all sorts of things, or they're having a tantrum like the guy in the video, it starts to get a lot more complicated to actually detect a head, the back of the head, or any kind of part, and see that that's a person, and that's the subject that you want to apply your effect on. So we turned to deep learning techniques because the traditional computer vision was failing us. If you're hearing this as a disclaimer, it's probably because it is. So I'm trying to say that we didn't so much hop on the deep learning hype train as much as we were pushed onto it because of the targeted use case we had. We wanted that extra flexibility. So what in this journey we discovered was essentially this, that the work that you need to carry out to deploy a neural network model on your phone starts way before you actually write any line of native code. I may have the attribution wrong, but ignore it, the quote still stands. So what we were asking ourselves was, well, okay, there's tons of detectors out there, right? What architecture should we use? How do we actually deploy it? How do we train it? So how do we choose? And that's what I would like to share with you, the approach that actually worked for us, and that made us be able to test different things every single day, instead of having to run models and run trainings for a long time and maybe lose our minds in the process. I'll go through the different phases that we went through and how this was configuration driven, as in each and every step was depositing a part of the information in a deployment file that's actually what went to the phone when we wanted to run our model. And I'll go over a few of the pitfalls and talk about how we avoided them. So this pipeline will look fairly familiar. Essentially, you first need to find a design that works for you. You need to design your model, your architecture. You need to prepare your data. You need to decide what data you'll need and pre-process it. You need to do the actual training. After that, you'll get your actual weights, the ones that you want to load on the phone. But you first need to evaluate which one of all those thousands of trainings that you've run will actually work for you. And yeah, eventually, all of that will go in your deployment file, and that's what you can use on your phone. So I'm going to stop here and ask who has worked on computer vision and is familiar with detectors and classifiers? Raise your hand. OK, fairly good. So, but this is fairly basic for most of you, I guess. A classifier will propose what the label is for a given content. So it'll look at an image and say, yep, this contains a person, or yes, this contains a dog. Whereas a detector is in charge of actually proposing a region for that label and a bounding box around the object. So that's two tasks. But inside it, you can actually see a detector as a classifier and a localization module on top. So the classifier, sure, needs to come up with labels it's been trained to know. So if it knows 1,000 classes, that's exactly what it will be able to predict. But then the localization module will need to come up with suggestions of where exactly inside your image is that object and what shape it has. And actually, those two things, classes and the pre-shapes that you can use, or the templates that you can use, affect the size of your model immensely. So again, this needs to be deployed on a phone. So if you're going to be deploying on a supercluster, then you don't need any of this. Sure, go have fun. If you're going to be deploying even on your laptop, that's fair enough. There's tons of architectures out there that run way over real time on a laptop, on the laptop you use at work, at home, that costs nothing on the market. But if you're going to be running it on a smartphone that perhaps, sure, a few of them have 3 GB of memory, but usually you'll have, what, 1 GB, 2? And the computation power is way less than the 1060 that'll be on your laptop. So you're definitely constrained. But on top of that, if you're aiming, again, at an augmented reality app, eventually you're going to want to integrate it into an engine such as Unity, right? Because you need to get your digital effects on that. So that means that if you're aiming at the 30 frames per second for the user, definitely your detector cannot run in less than, say, 40 to 60 FPS. So you really need to get that very slim and very quick. So the first thing we did was, OK, what's out there? What can we use? Where can we start? And luckily, there's a paper published last year that actually did a ton of that work for us. I encourage you to read it if you're curious about different architectures that are competing on ImageNet. This paper is great. And it's basically a survey of available classifiers. And on the x-axis, you have the operations needed for a single prediction and a single image. And on the y-axis, you have the actual top one label accuracy. And the size of the circles is proportional to the actual parameters, to the complexity of your model. So the bigger the circle, the more number of parameters on your model. So given that we wanted to deploy on a phone, we definitely did not want to have hundreds of millions of parameters. So part of that was definitely out. We're actually aiming, so to give you a rough idea, those VGG there, you see it's 200 and almost 200 million parameters, 100 and something. That translates into several hundred megabytes. And we're actually aiming at a size of, say, 5 megabytes. So 1 million parameters, 2 million parameters maybe, tops, is what we wanted. And the same applies to operations. We cannot go too far to the right, that's for sure. So what we want is maybe a family of classifiers that you see in the still white area, and we wanted to boost the accuracy and slim it down further. So going back to the classifier versus detector thing, if your detector is going to be at least 50% a classifier, if that is going to be so important in the size and the speed, you definitely need to start by working on that. So you're aiming at reducing the memory footprint and the inference time. So what is the usual suspect for parameters in a model? For instance, fully connected layers just kill you. And if anyone was here this morning when Tal was talking about convolutional methods on text, you see that convolutional layers come up again because they're great. You can actually translate your fully connected layers into convolutional layers, and that will save you tons of parameters. So one, you look for an architecture that is convolutionally based. And the other is if you have layers that the architecture of choice is not originally a convolutional, you can translate your fully connected layers into that. But then you also have to think about inference time, right? So a usual trick is, okay, let's reduce the input size and see how our model performs, if that kills the accuracy or if it'll stand. And there's other things that will also reduce the rest of the layers, and I'll go back to that in a second because, for instance, classes affect the size of your layers, and you want to keep that small. Because, again, in the localization module, there's two big things that will make your model bloat. One is the number of classes, and the other is those template boxes that the model produces to predict the bounding box around your subject, right? So if you reduce those two things, your localization module will also slim down, and that will help you. And then there's a notion that I'll get back to a bit later on, and it's the keep only what you need. So when you're getting a model, there's a bit of a cargo cult going on in that you get it and you don't touch it because you don't really know how it works. Well, you need to start asking yourself what's inside that model and what layers you can actually do without actually breaking anything. So what exactly is that layer at the end doing, and can I lose it? If I remove it, what happens? If I change it for something else that maybe reduces its size, what will happen? So at the end of this phase, you basically have an architecture that you can, at least you think is promising. And that goes to that deployment file that you pass on. So at this point, you can think of it as a cafe proto.txt, if anyone's been doing cafe lately. It's just a definition of your architecture. And yep, at that point, you're ready to move through to your data. So you need to think what exactly your users are going to be using. So if you're aiming at a self-driven car, then the Kitty dataset is great. But, oh yeah, and you'll see it basically here, if I can see it. Not working. OK, it's not really powerful enough. Anyway, so this one here belongs to the Kitty dataset. So you'll notice that it's a fairly weird format. So if you're going to be deploying on an iPhone, for instance, that's got like a portrait aspect ratio and it's fairly slimmer, then maybe that will mess up with your results. You need to try it out. But in any case, if you notice the kind of data present in a car dataset is not going to exactly be the ones that you want to be using for an augmented reality app to use with your friends, right? So maybe the data set that contain pictures like the one above, where a bunch of people are pretending to be zombies at a bus stop, will match a lot more the kind of data set that you want. So that first step is, OK, let's see what exactly are we going to be using, what kind of data are we aiming at, what format do we expect, and then what free data sets do we have available to us. And those three, for instance, all contain people. They're freely available, free with conditions, as we'll see in a second. But they're absolutely great, especially Pascal and Coco, which are also challenges, are really diverse and are great. So yeah, you've chosen your intended use, you've chosen your format. But then you'll realize that since you're mixing and matching data sets, you won't expect them to all have the same format, right? That just doesn't happen. So you'll need to pay, not with money, but with time, re-annotating and translating everything to a format that you use internally in your team. And this goes back to another talk this morning, the golden standard data talk, where Miro was explaining about how you need to decide how you're going to annotate, for instance. And that was crucial for us, because you need to decide what actually is a detection, how you're going to be drawing your boxes, and you need to clean up your data before you ever dream of using it. And there's also a big part of this in consistency, because even if these data sets have very strong players behind them, they're not perfect, and you are going to find really disturbing things in them where people were just nuts when annotating them. So you really want to explore your data and fix it. Simply clean it up. So the first step is that, explore it. And the second is analyze it and extract statistics from it. Because when you load your input data on your phone, you're going to want to do things like normalizing it. And you're going to extract another very important piece of information, because, again, I'm going back to the predefined shapes. If you're going to be reducing the number of shapes that you'll be using, you want those to be representative of the actual boxes that you have in your target data, right? So you need to analyze it and come up with good representatives of what your data will be. And that goes to that deployment file, which you send forward through the pipeline. But before you move on, you also need to start tracking things like what subsets of your data set are you using to train. because maybe not everything is useful to you. Maybe part is actually confusing your network. And you also want to start tracking the augmentations you're applying to your data while you're training. But with that, you're fairly ready. You've got your statistics on the deployment file, and you can move on. And you can actually start training. Great, because there's one thing that's kind of known for deep learning, and that's it requires a humongous amount of data. But what you should remember is that it doesn't have to be your data. There's no need to train from scratch unless your problem is so specific to you that no one has ever trained any model before that. And at least for object detection, there's several challenges like ImageNet, like Coco, like Pascal, where people have already trained very expensive models and published those weights. And you can piggyback on that. There's no shame in that. So don't go at it alone. Just take one of the pre-trained models, for instance, for those classifiers, and use transfer learning. Because one thing that holds for neural networks is that the very early layers of any network is a lot more generic. So those layers are learning things like edges. They could be like hair-like features. So if you can reuse that, because after all, an edge is an edge, whether you're detecting breeds of dogs or people, right? It's still an edge. Whereas the later layers in any network will be a lot more specific, and those are the ones that you will want to retrain. So that's why in the figure you can see part of the network that has been frozen, which is fairly simple to do in Caffe or in TensorFlow. You freeze those layers, and those are the ones that are not going to be retrained because you trust them. Those have been probably trained over ImageNet, which has millions and millions of images, and you just retrain the later layers to your specific data set. So Coco, or if you're able to collect data from your users, data from them. And at this point, as usual, you want to track absolutely everything you try out. So if the hyperparameters you're using to train need to automatically go into those traces, and because you'll need to evaluate whether they are hurting your training or whether they are actually working for you. And it's not about going fancy and getting a wonderful framework that does have hyperparameter tuning for you. And that's perfectly nice. If you've got that available to you, by all means, use it. But the only crucial thing here is that you actually start doing it. So if you're using Jira for tickets, you can use that to track the hypothesis you're going to test for your experiment. Well, I'm guessing that this data set will work better because blah. Okay, do that. If you're using Redmine, cool. If you want to just during training dump everything you use into a CSV, that's perfectly fine, because after all, any CSV you can feed to any more sophisticated tool and extract insights from it, so it's fine. Just start doing it. So at the end of the training, what you get is your actual trained model. You get the weights, you serialize them, and that's what you'll be deploying on the phone, aside from all the description of your network and everything that you'll be serializing as well in that file. So one thing that you'll want to do is evaluate, but what are you going to be looking at? Because at least for me, as soon as you get a detection, you run your model for the first time on images, and you go, wow, look, it's detecting, it's working, right? It's perfect. But then you run it again, and it picks up the body, but it doesn't pick up the head. And then someone comes up to you and say, well, yeah, sure, the first one seems to be working better because, sure, it picks up a body and it picks up a head, whereas the other one doesn't. But have you noticed that the head box takes like part of the torso? That doesn't seem right. So, yeah, that means that you have to go back to training. And it's even worse with some other images where it's really not that clear. And in any case, you definitely do not want a human to sit in front of thousands of images for every single one of your hundreds of experiments. That's just not feasible. So clearly you need to go all full data scientist and adopt a metric. And a very popular one is just a simple precision recall curve, where you want to make sure you're minimizing your false positives and your false negatives. And of course, you're going to be aiming at that top right corner, the 1-1, where you're supposedly not missing out any of the detections that you're meant to be detecting, and you're not producing any new ones that are just not there. And if you'll notice, every single of these points are one model and one combination of parameters that we were testing. And we know that our perfect model will sit somewhere around up to the right. And yeah, this is just a sample of a whole ton of models we were testing in sane. So yeah, what things will you want to be looking at? You definitely want to be tracking the architecture that you were testing out. You'll be tracking the data sets that you were using, because you'll probably want to mix and match, or you want to maybe remove parts of those data sets because you think they might be confusing the network. All of that needs to be tested so that at some point you know what's actually working. The augmentations you're using will vary depending on your targeted use. The hyperparameters and the deployment parameters. By deployment parameters, I mean things like the confidence threshold. So sure, you've got a prediction, but what's the minimal threshold to consider it really a human? And so all of that is what you're going to try to be evaluating. And you need to be particularly careful because the validation sets could also be biased, very much so. Or even not mirror the conditions that you want to be working in. If you know that your app is going to be used at night, then maybe you want to make sure that your validation set contains tons of night images. Otherwise, you just won't know which one works best. But in any case, if there's one takeaway from all of this, at least for me, in this journey, it's that you don't want to rely only on the metric or only on human eyes. You need to rely on both. You actually don't want to say, okay, this has the best mean average precision, so this is the best model. Not quite. You still need to run it over quite a few images and let someone else look at them, and especially if it can be deployed on the phone, and see if the model is actually behaving smoothly and if it will solve your actual problem. But in any case, cool, you've reached your evaluation, you've got your best combination of parameters, and you're ready to deploy. So the key part here is that every day there's some announcement of a new framework. I'm not sure if anyone has tested out TensorFlow Mobile. I'm really interested in knowing your opinion, if that's working out for you. We haven't tested it yet. We're working with Metal. Cafe 2 uses Metal under the hood, and we were targeting iPhones. So obviously, Metal performance shaders is what's working for us. But the key point here is to try to find a framework that has layers that you want to use, because if you choose a certain framework and things are missing, if you want to implement the latest, I don't know, the latest paper from Facebook, and certain layers are just not there, then you're going to have to rewrite them from scratch. So that's extra time that you need to plan for. And above all, what you do want is, as soon as you have any part of your network ready, or more or less thought of, implement it and deploy it on the phone. And make this a very fluid loop where you are designing, training, evaluating, and profiling on the device very quickly. Even if you don't have your detector ready, even if you only have the classifier, be sure to deploy it on the phone and test it out on friends and see if it makes sense, and above all, if it's fast enough. Because again, if your classifier is way too slow on the phone, sorry, if it's running at 7 FPS on the phone, then there's no way your detector is going to reach those 60 FPS. So before I finish, I wanted to take a look at some of the pitfalls that we found, or more how we avoided them. And the biggest one to me would be the data sets, because again, you need to sanitize them. We found things where the annotations were definitely not consistent. Even within the same data set, all those freely available ones are great. They're the best that you'll find without having to hire someone to actually label every single thing. But you'll find that not all the people on an image have been labeled, or maybe crowds were just labeled as one huge blob, and, well, that's supposed to be a person. You'll find that some detections are missing, or even what exactly should go into a bounding box. So, for instance, your head bounding box. If someone has very long hair, should their hair be completely inside the bounding box, or what do you define? And in any decision that you make, you need to make sure that everyone's on board, and if you're relabeling your data, it needs to reflect those decisions. And a particular problem that we found was, for instance, when we were playing around with Kitty. Kitty has cyclists, right? But then other data sets have bikes and have people. So what's a cyclist? And if you have a bounding box that englobes the bicycle with a human on top, you probably need to go through all of your labels, all of your images, and relabel them, right? Because you need to separate the cyclist from the... So you actually have to detect people to relabel data that you're using for training to detect people. That just doesn't work. So you need to get creative about it. More pitfalls, the evaluation. Again, I'll just come back to that. You really want to be evaluating in several ways, not just a metric. Metrics are great for challenges. That's how you beat at ImageNet or the Coco challenge or whatever. But if this is going to end up in a user app, you definitely want humans taking a look at videos and seeing if your detections make sense and if they feel good, if the bounding boxes actually fit the subject, because you should probably be paying attention to that precision recall and maybe how the overlap, so for instance, the intersection over union of those bounding boxes. But you also want the human feeling of, does this look right? Even if it's just over a very, very small subset. You also don't want any humans involved in any part of the configuration. Humans just break things, that's known. So you want all of this to be automatic. And you want to be systematic when you're tracking your experiments. That's a given. And again, early profiling on the phone saved us a lot of time, even if it was just part of the network, just running and taking a look at the output activations, if they made sense. So if you're taking a picture of a mug, and that has to be labeled a mug, even if you don't have the full thing running, the activations should look good. And if already just a part of your network is running way over your targeted FPS, then that's just not going to work. So yeah, so to sum up, we've seen a few tips at actually choosing your model. This pipeline that's based on a configuration that's completely automatic so that no human will break anything, and that will help you finally deploy on your phone, and a few of the typical pitfalls. So yeah, thank you, and any questions?
Excellent. Thank you so much. I hope that there are some good questions. So if you have a question, please raise your hands. Jeffrey will come around. Okay, I will wait for you.
Thank you. Hello. Hi, over here.
Sorry.
Yeah. Thanks for the presentation. It's great. I have a question about the libraries, the image recognition libraries. You mentioned ImageNet.
The what libraries?
The image libraries, the data sets. Mm-hmm. You mentioned ImageNet.
Yeah.
Could you repeat the others, especially the ones that have different sets of objects?
Yeah, sure. So they're all...
Thank you.
ImageNet is also something you can download if you want to train from scratch. Here. You probably wanted to see this, so if you want to take note. Kitty is meant for self-driven cars. Pascal and Coco, well, Pascal is a bit older. It's from another challenge. And the ones that I like best, personally, are Coco and Pascal for day-to-day pictures. So they feel more familiar, more the kind of pictures that anyone would take with their phone or with a camera. Kitty is very, very specialized. It's great if you want to be detecting cars, bicycles, trucks. That's what you want to go for. And yeah, they're all freely available and with different formats. That's my gripe.
Okay, next question over here.
Fantastic presentation, and congratulations.
Thanks.
Not too long ago in Ghana, I don't know how you've been following issues in Africa. A captain was murdered too badly, and they have to track the mob in detecting who actually led in the murdering of the captain soldier in Ghana. 35 to 40 people was arrested, and the video that was shown is like there was no techniques to actually detect who did what. And that is the kind of challenges we researchers in Ghana are actually facing when there's a mob attack and there's a video, the images, how to actually crown down the person who actually did that. So you take the matter to court and the case is thrown out because there's no real evidence. How would this, your research, actually help us, both the academic communities and the security agencies, to actually crack down mob attack or murdering through mob?
Okay, that's a very fair and very good question. So there's two things that you might want to look into. One is scene analysis, and that's a very active topic where people actually are trying to interpret what's going on in an image. It's not just object detection, which is what this is about. It's actually seeing a video feed and interpreting what is going on. If there's detection of several people moving in a common direction towards one single person, then maybe that's a potential attack. I'm not completely familiar with that topic, but maybe you want to read into it. There's another thing, you mentioned that they didn't actually know who had done the mobbing. So you want maybe to look into re-identification, because it's not just about detecting what a person is or where they are, but realizing that one person is the same here than here. So if you've got, for instance, a database of pictures, seeing that the person in the video is the same that you have in your database. So it's two related, but not exactly the same topics. And in any case, this could help. For instance, if you have an IP camera going in places where you know people shouldn't be there, or I don't know, if you're in your office and you know that not more than you and maybe someone else should be there, if the count of detected bodies goes way up, then maybe there's some mobbing going on, or in parking lots, or, you know, probably counting people might help you. But this, to be honest, this was meant only for entertainment. So this is just for an entertainment app. But there you go. There's those two other topics that you might want to read into.
Just a very quick question. How long did it take from the beginning to the very end for this project, from sort of conception to having the model deployed on the phone?
Well, the full journey, maybe a few months. We started out trying out with traditional computer vision techniques, and we actually have a prototype running on that. But then very quickly we started trying out models to be able to do this. And the final app is launching, I don't have the actual date, but any day now.
Okay, as the app is not ready yet, maybe it's not sure, but are you trying to get more training data from the use that people will make of the app? For example, if there's some clip they want to share where there are these boxing hands at the head, for example, would you try to get this as, okay, it looks like our model worked well there, so we can use this as training data? Are you trying to get training data from the use of the app?
Ideally, yes. There's a whole ton of legal issues associated to that. So retrieving data from your users is tricky. But yes, that's something we would like to do. It's extremely useful because it's exactly the kind of data that you want to train on.
Great talk. You talked about how you basically track the versions, how good they are, the different experiments.
Tracks the versions of, could you speak?
The experiments track the versions, like how good the models are performing and stuff.
Yep.
But if you have like dozens or hundreds of models, that's kind of tricky. And you said, yeah, do it, and that's right. But do you have any good best practices there? Any recommendation how you should do it? Or how you actually do it, maybe?
Yeah, so doing it incrementally helps out a lot. So there's many of the experiments, after all, are about testing one hypothesis. If I turn on this, does it help or not? So you want a control model and a completely equivalent model with only that thing activated. So that means that you don't have to run, if you have maybe 100 models already trained that can produce themselves 100 more models if you tune the parameters, then you don't want to do that. You just want to pick out maybe a few well-known models, activate that feature that you want to test, and see the result and see if it's significant the change that you observe later on in the evaluation.
Hi.
Hi.
I was wondering, since you've tested hundreds of models, you were showing in the plot of precision versus recall, I guess a lot of them just differ by the architecture, like number of layers, number of neurons per layers, number of frozen layers. Others might differ because of what you were saying of choices like hair, no hair in a head, etc. I was just curious, what is the most surprising thing you came across there? If you can name any. In terms of like things that turn out to be efficient, which you wouldn't have expected, or things you thought would have worked well and did poorly.
Well, some of augmentations are unreasonably helpful. Some data sets are really, really bad. So for instance, I can flat out tell you that I expected Kitty to work very well for us because we were processing it in a way that the format matched what we wanted. So we weren't just feeding that huge thing inside the network and then expect it to work on an iPhone format, but really wasn't working. And by digging, we realized how badly annotated it is for our purposes, how badly humans are annotated. And then there's a ton of things that surprised me. Like if you're playing around with the segmentation part of Coco, you'll find where people just went nuts and decided and hated their lives while annotating and just wrote absurd things. So yeah, you see all sorts of things.
We have time for one more question.
So thanks for the talk. Is it faster to train a neural network using transfer learning than to train it from scratch?
Yeah, very much so. Yeah, sure. Because if you're training if you've got most of your network frozen, then the backpropagation only reaches a certain point. So it's a lot faster. It changes from, if you're trying to retrain the full thing over ImageNet, it might take several days, weeks. Whereas our models, for instance, training just a few layers take hours. Yeah.
Excellent. So can we give one more round of applause?